Alright, in this video we're going to discuss extrema on an interval. So first let's start by defining extrema. So we're going to look at the definition of extrema. First what we're going to say is we're going to let f be defined on an interval. We're going to call that interval I containing c, containing a value c. What we can say then is f of c is the minimum of f on the interval when f of c is less than or equal to f of x for all x values in the interval. We can also say that f of c is the maximum of f on the interval when f of c is greater than or equal to f of x for all x in the interval. Some more things we can say are that the minimum and maximum of a function on an interval are the extreme values or the extrema, which is plural, the singular of which is extremum of the function on the interval. We can also say the min and max, minimum and maximum, are also called absolute minimums and absolute maximums, or global minimums and global maximums. Extrema can happen at interior points or endpoints in an interval, and if they happen at endpoints we call them endpoint extrema. We do have a theorem for today. Our theorem is theorem 3.1, which we are calling the extreme value theorem. The extreme value theorem says if f is continuous on a closed interval from the value a to b, then f has both a minimum and a maximum on the interval. Let's also throw in a definition. We're calling this the definition of relative extrema. And there's going to be two parts to this. The first part says if there is an open interval containing a value c on which f of c is a maximum, then f of c is called a relative max of f at the point c f of c. The second part of this pretty much says the same thing, but we replace the word maximum with minimum. So if there is an open interval containing C on which f of c is a minimum, then f of c is called a relative minimum of f at the point c f of c. So now let's take a minute and we're going to check out our first example. And what we're going to do in this example is we are going to find the derivative. So this is example 1. We're going to find the derivative at each relative extremum. So, in the first one, and I have a picture I'm going to pull up for this one, we are going to look at the function 9 times x squared minus 3 all over x cubed, where our relative maximum is at the point 3, 2. So the whole point of using the derivative at trying to find, or when finding relative extrema, is when we have this, we are looking for a spot where the slope is 0. So we use the derivative because that is how we find the slope at a given point. So let's start by finding the slope of the function they gave us. Now this is a quotient. We're going to use the quotient rule, where here at the top of our function, if we wanted to call that f, we could, and at the bottom of our function, we could call that g. So we're going to take the denominator, using our quotient rule, x cubed, so f prime of x. Give me a second, I'm going to erase this. F prime of x is equal to the denominator times the derivative of the numerator. Well, 9, that's just a constant multiple, so we can rewrite 9 times the derivative of x squared minus 3 is going to be just 2x. Minus, we take the numerator. We've got 9 times x squared minus 3 times the derivative of our denominator, which is going to be 3x squared, divided by our numerator, our denominator, x cubed squared. So let's clean it up. In the first term in the numerator, x cubed times 9 times 2x, that is 18x to the 4th. If we go and multiply 9 and 3x squared and then also distribute it, in fact, before we distribute, let's just multiply 9 and 3x squared. So we're going to have minus 27 x squared times x squared minus 3. We'll distribute the 27x squared in our next step. That's all over. Powers of powers tell us that x cubed to the power of 2 is x to the 6th. So let's clean it up a little more. We'll distribute this negative 27 into the parentheses. So we're going to have 18x to the 4th minus 27x to the 4th plus 81x squared all over x to the 6th. But there's still more we can clean up. We can clean up Well, we can combine 18x to the fourth minus 27 x to the fourth. So we're going to end up with I'm going to write it more under our picture. Negative 9x to the fourth plus 81x squared over x to the sixth. And since all the terms have an x squared, let's go and eliminate an x squared. So we can write this as negative 9x squared plus 81 divided by x to the fourth. And since they wanted us to, we found the derivative, so we found f prime, but they wanted us to find the derivative at the relative extremum. Our relative maximum is at the point 3, 2, so we're going to substitute 3 in for x. So we're going to have negative 9 times 3 squared plus 81 all over 3 to the fourth. 3 squared is 9. 9 times negative 9 is negative 81 plus 81 over, 3 to the fourth, that's 81. Which is going to give us 0 over 81, which we know is just 0. That's going to wrap up that first part of this example 1. We're going to look at 2 more pictures. The second example we're going to look at is the function, the absolute value of x, which has a relative minimum at the origin. We didn't learn a process to find the derivative this way other than using the limit process. So we're going to look at the limit of f of x minus f of 0 over x minus 0 as x goes to that minimum from both the left, and then we're going to also look at it from the right. Now, from both of these limit processes, we're going to find that our derivative is the absolute value of x over x. And if we were to plug 0 in, we're not going to find something that works. So what I would do is I would take my calculator and I would graph these. We're going to see that this first limit is going to approach negative 1, and the second limit is going to approach positive 1. And since both limits are approaching a different value, we have to say that the derivative at the point, at that extreme maximum, does not exist. Just at that one spot, the derivative does not exist. There is no slope at this point on the picture. Alright, and so our last part in this example, this first example, is we're going to look at the function sine x, the sine function, and it actually is going to have a relative maximum and minimum. The relative maximum here is pi over 2. The relative minimum is 3 pi over 2. So the first thing we need to do is find the derivative. If f of x is sine of x, then f prime of x, we learned in our last chapter, is going to be cosine of x. So now what we're going to do is find f prime at pi over 2 and 3 pi over 2. F prime at pi over 2 is going to be cosine of pi over 2. And using our unit circle or just plugging this into a calculator, we'll find that cosine at pi over 2 is 0. So we found one value. We also have to find f prime at 3 pi over 2, which means we need to find cosine of 3 pi over 2. Which again, if we use our unit circle or just use a calculator, we're going to find that the value is 0. This is going to wrap up our first video in this Extrema on an interval lesson. I do think we can get the rest of it done in our next video. So let's see.